Hi guys, welcome to the notes for 3-4. It's titled, Can Two Transformations Be Equivalent? Today we're going to be stretching exponential functions. The little paragraph below says, in the beginning of the chapter 3-1, you investigated and compared horizontal and vertical stretches. You can now shift and stretch graphs both horizontally and vertically. In this lesson, you will see how two different transformations of exponential functions can be equivalent. So we're going to try to apply different transformations and see if we get the same graphs to our functions. This first part says, write the rules for the coordinates in the following transformation to the graph of function f. We have y equals negative 1/2 times f of 3x plus 4 plus 7. All we're looking to do is create the rules for the transformations. As we look at this, we can see that there is going to be a vertical compression, and it's going to be flipped vertically and shifted up 7. Remember, those all will be happening to our y values. So we'll put negative 1/2 times y plus 7. Looking inside the grouping symbol here where x is located, we have 3x plus 4. And we need to do the inverse of what's happening in there. So just a quick reminder, if you don't remember how to do it, all you're going to do is write it out, set it equal to y, flip-flop your x and your y, and then solve it for y. So you have x minus 4 is equal to 3y, divide each side by 3, and you have x minus 4 divided by 3. Some of you are probably to the point where you can just look at this and figure that out, right? You say times 3, then plus 4. So you have to undo the plus 4 by subtracting 4 from x, and then you're going to undo the multiplying by 3 by dividing it all by 3. Either way, you get the same answer. Let's move on. Can two different transformations produce the same result? Consider the parent graph y equals x squared. Let's do that real quick first. Let's set up a table for y equals x squared. We usually use -2, -1, 0, 1, and 2 in our parent graph, so we'll put those on the table. We'll square them to get 4, 1, 0, 1, and 4. And now it asks us to write the rules for the coordinates for each transformation. So the first transformation that's occurring is y equals 9 times x squared. So a vertical stretch. Our rules for this one then would go from being xy to, well, nothing is happening to x, right? X is still, isolated to say. So x is going to stay the same. This 9 times the x squared means like it's an a value. So it's our vertical stretch. So we're going to say 9y. Let's just make a little table to look and see what happens. So x's are going to remain the same, and then we're doing 9 times our y values. Since x is going to end up being the same, right? These are our x values. We're just going to put those into our table. -2, -1, 0, 1, and 2. Now we'll take our y values, and we're going to multiply them times 9 and record them in the table. So 36, we have 9, 0, 9, and 36. Again, that's our y values over here being multiplied times 9. Now let's look at the second transformation that they've given us. We have here y equals the product of 3x squared. If we were to write out our new rules for our coordinates, we'll notice here that x is being multiplied by 3. So remember, we have to do the inverse. So we're going to divide x by 3. And then there's nothing happening to y, so we'll leave it as x over 3 comma y. We'll set up our table. Let's do x divided by 3, and then our y's. Since our y's are the same, let's go ahead and just copy those down first. Remember, they're coming from over here at this table. So 4, 1, 0, 1, and 4. And now we're going to take each of these x coordinates, and we are going to divide them by 3. So we have negative 2 divided by 3, negative 1 divided by 3. 0 divided by 3 is 0. And then we've got 1 divided by 3 and 2 divided by 3. So you're probably asking, what have we done for ourselves here? Okay, well, we want to see a comparison of these results. You'll see we have this set of values, we have this set of values. Okay, you will see that we do have 0, 0 on both of them, right? But none of the other inputs really match, right? We've got different inputs in each of them. We have negative 2, negative 1, and positive 1, and positive 2. Here we've got fractions, right? These values are all kind of, lodged in between here, right? Between negative 1 and 0 and 0 and 1. But if we take our graphing calculator and we get it out, we can actually compare these a little bit easier by graphing it. So let's type in the first one. We have 9x squared. And the second one, we have the product of 3x. And then we're squaring all of that. If I graph those, you're going to see I get a parabola. But there's only one parabola on the screen. And the reason why is because these two functions are actually equivalent to each other. If I go to my table, you will see that all of the outputs between them match. Okay, and I'm sure you probably already recognized it on your paper. If I take y equals 3x and I square it, right, that's like saying 3x times a 3x, or 3 times 3 is going to give me 9, and x times x is going to give me x squared. So this is really the same thing as y equals 9x squared. So the tables don't look exactly the same, but that's because we are using different input values on each of those tables. But the functions are actually equivalent or the same. Okay, so our vertical stretch actually was the equivalent of our horizontal compression on this one. All right, let's look at another one. It says determine the parent function for the function below, then graph the function in two different ways. Y equals the square root of 4x. Well, we know our parent is going to be y equals the square root of x. And when we do y equals the square root of x and we make a table, we usually use 0, 1, 4, 9, and we'll even throw 16 on there. Those are all perfect squares, so we end up with 0, 1, 2, 3, and 4 as our outputs. Well, let's look at what transformation is happening and make a new table for our y equals the square root of 4x. And then we'll make another one after that, right? Because it says to do it in two different ways. If I'm trying to write out rules here, I've got x comma y, and my transformation that's being applied is going to affect my x's. Right, I'm taking 4 times x, which means in my inverse I'd have to say x divided by 4. And then nothing's happening to y, so we'll leave it as it is. Let's make a little table. We have x divided by 4 and our y's. So since our y's aren't changing, right, I'm going to go ahead and just copy those down. 0, 1, 2, 3, and 4. And then we're going to take each of these x coordinates and we're going to divide them by 4. So 0 divided by 4 is 0. 1 divided by 4 is 1/4. 4 divided by 4 is 1. 9 divided by 4 is 9/4. And then 16 divided by 4 is 4. Let's take those now and let's plot them. So 0, 0, 1/4, 1, 1, 2, 9/4 is like 2 and 1/4, and then we're going up to 3, and then we have a point at 4, 4. So even though they're kind of messy looking, it does make our points go in a nice square root curve just like that. Now, how do we create another function from this? Well, let's take our y is equal to the square root of 4x, and let's simplify it. This is the same thing as the square root of 4 times the square root of x, we know that we can, separate square roots. And I can take the square root of 4 to get 2. We could say y is equal to 2 times the square root of x. And let's look at that one. If we're trying to create new rules here, we have x comma y would become what in this case? Well, it doesn't look like anything is actually happening to x here, so we could say this is just x. And it looks like we're going to multiply everything times 2, so our y would be 2y. So that's a different rule, right? When we look at these, this is one rule, this is a different rule, but really it's the same function. So let's see what happens here. Let's make a table. In this case, our x's will remain the same, and then we're going to multiply each of our y's by 2. So take your x's, here's your x's. It looks like we'll just copy them right in on the table. 0, 1, 4, 9, and 16. And now we're going to take each of these y values, and we're going to plug it in here and multiply it by 2. So we should have 0, 2, 4, 6, and 8. Now, will they all fit on the graph? No, but let's get on there what we can. 0, 0, 1, 2, and 4, 4 all fit on there. And when we make that curve, you're going to see the exact same graph that we have on the left side. So while our tables aren't exactly the same, okay, they actually are of the same function. You can see a few of the values that show up on both though. We had 0, 0, 1, 2, and 4, 4 appear on both the tables, which will also help us to be able to see that these are equivalent transformations. So let's define that at the bottom. Let's say equivalent transformations okay, these are going to be two different transformations that result in the same graph. So again, two different transformations that result in the same graph. All right, let's move on. Now we're going to apply some of our properties of exponents that we know to show that the following statements are true. You'll see here we have 2 times 3 raised to the power of x plus 1 should equal 6 times 3 to the power of x. Okay, so if we think back to our exponent rules, if I gave you something like a to the 6th times a squared, you know since we're multiplying two numbers with the same base, we can add the exponents together. Right, so we get a to the 8th power. And we're so used to going this direction, but you can go back this direction too. Right, I could take a to the 8th and separate it into a to the 6th plus a to the power 6 plus 2, sorry, lost my wording, and then break it apart to get our answer. So this is exactly what we want to do in our expression on the left. Let's treat this as 2 times 3 to the power of x, and instead of saying plus 1 up there, let's do times another 3, and this time to the first power. Think about how that simplifies to give us this. Now we're breaking it apart. So we really have 2 times 3 to the power of x times 3, and if I reorder it using the commutative property, I have 2 times 3 to the first times 3 to the power of x. I can actually multiply those together to get 6 times 3 to the power of x. And that's exactly what we were trying to get it to look like. Okay, now you can use other properties of exponents as well. Remember your property where you've got, say, a to the 4th power, and you're raising it to the 3rd power. We know that we can actually take it and say that's a to the 4 times 3rd power, or a to the 12th power. Okay, and again, we're used to going this way, but we can actually take it and go back this way as well. So as I look at 3 raised to the power of 2x, I could think about this as being 3 squared raised to the power of x. What's that do for me? Well, I can take it and I can simplify this. 3 squared is actually 9, so I have 9 to the power of x, which really is 9 to the power of x. Okay, so we're going to use some of these properties to help us rewrite some of our exponential functions. So it says, consider k of x equals 3 times 2 to the power of x plus 2. Describe the transformation from y equals 2 to the power of x to y equals k of x. In other words, write the rules for the coordinates. All right, so if we're thinking about it as being the parent function, y equals 2 to the power of x, we're saying, well, what's happening up here, with our 3 and our plus 2, our rule would go from being x comma y to, okay, so we're going to have to do the inverse of what's happening to x, so this would be like x minus 2, and then we'd be doing 3 times our y value. That is our new rule for our transformed coordinates. Okay, so then it asks us to rewrite the function k so that there's only one transformation required. What's that mean? Well, you look up here, we're applying 2 different transformations. They want us to break it down so it's just one. So let's use what we did in the previous slide, where we have our k of x is equal to 3 times 2 to the power of x plus 2. And let's break this apart. So we have 3 times 2 to the power of x. And remember, this plus 2 comes from multiplying it times another 2 to the second power. Well, this one's the same thing as 4. So if we rewrite this as 3 times 2 to the power of x times 4, we can actually use our commutative property and do 3 times 4 times 2 to the power of x, or 12 times 2 to the power of x. So this should be equivalent, right? So what's our rule that's going to happen here? Well, this would be x comma y, and it would become, let me look at it, right? X is by itself, so we'll throw our x in right there, and then this would be comma 12y. But this is for our parent function, y equals 2 to the power of x still. Now it says check by graphing both in the same viewing window. So let's do that one more time here. So let me pull that graphing calculator out. Let's go to y equals. We'll clear out what we have in there already. And let's do it. We have 3 times 2 raised to the power of x plus 2. And then down below, we're going to have 12 times 2 raised to the power of x. We graph them both, and you'll see only one curve on your graph. So remember, you can also go in and look at your table, and you'll see that all of the outputs are the same. If they're not, you've made a mistake. Okay, so please feel free to ask if something like that happens. All right, just a couple more. Let's get through these. The next one says, if g of x equals 2 to the power of x, describe the following transformations to the graph of g. Write the rules for the coordinates. So the first one, we have h of x equals 3 times 2 to the power of 3x plus 3. So we know we're starting with the coordinates x, y, and we need to just write our new rules here. Looking at our x's, we need to do the inverse of this. So since we're multiplying times 3, then adding 3, we have to subtract 3 first. So I'm going to say x minus 3. And then we undo the multiplying by 3 by dividing it by 3. You can also take it and do, set it equal to y and find the inverse that way. And then for our y values, you'll see that we have just this times 3. So we have 3 times our y. Now they're asking us to rewrite the equation using the properties of exponents, then write rules for the coordinates for the new equation. All right, so we can do that here. Let's just recopy our equation below. H of x equals 3 times 2 to the power of 3x plus 3. So if we're just trying to use those properties of exponents, Okay, let's keep it right now as a base of 2. So we're going to say 3 times 2 to the power of 3x times 2 to the third power. We know 2 to the third power is 8, so we have 3 times 2 to the power of 3x times 8. Rearrange it and you'll get h of x is equal to 24 times 2 to the power of 3x. Okay, so we're still using our parent function right now as being like g of x is equal to 2 to the power of x. Okay, so our rule in this case then, if you're thinking about it, would be from x comma y to, if we're multiplying our x times 3, that means we have to do the inverse, so we're going to say x divided by 3, and then we have 24y. Now let's say, for instance, that somebody wanted to do something a little different here, right? They noticed this, and they wanted to use those properties of exponents to break it down more. You can, right? We could take this and say h of x is equal to our 3 times 2 to the power of 3x plus 3, right? And we've already broken it down to 24 times 2 to the power of 3x, right? So we did all this stuff in the middle. But now they wanted to take it a little bit further by applying another one of our exponent properties. They could say this is 2 to the third power raised to the power of x, and we're still multiplying it by 24. So now we have 24 times 8 to the power of x. Now there's even less transformations happening, right? You can only see one transformation. But if you're going to do this, here's what you need to do if you're writing out your rules, right? You're going to have to list your parent function as y equals 8 to the power of x. That way it makes more sense if we're applying our rules to our functions. You could say, well, there's nothing happening to x at this point, right? There's nothing happening to x. So we've got x here. And then the only thing that's happening to y is we're multiplying by 24. So you have 24y. So this makes sense as long as you've listed the parent function is y equals 8 to the power of x. That's important to know. This rule occurs only when our parent function is g of x equals 2 to the power of x. All right, one more set. Let's go. Let's look at the last one. Let f of x equal 3 times 4 to the power of x. It says, describe the transformations for each graph by writing the rules for the new coordinates. Are the transformations equivalent? The first one they give us is y equals f of x divided by 4. So it looks like we're taking our function f of x from above and we're dividing it by 4, which would be like a vertical compression. Right? If I wanted to take this here and think about it as I was dividing the whole entire thing by 4, I'm saying, y is equal to like 3 times 4 to the power of x divided by 4, right? I'm just substituting in this for that. So you see this down below now. Okay, well, I could rewrite that as like saying 3/4 times 4 to the power of x. So when I have an equation that looks like that, right, my parent function, y equals 4 to the power of x, what's happening? Well, we've got our points, x comma y, would become x comma 3/4 y, right? Because this is like our stretch factor that's out here. So applying that vertical compression, okay, they want to know, is that going to be the same as if we subtract 1 from our x's, which we know is going to be a horizontal shift to the right? That'd be 1 unit. So is a vertical compression, like we're doing there, going to be the same thing as our horizontal shift to the right 1 unit? And we'll just have to check and see, right? Let's go ahead here and let's rewrite our equation. That would be like saying y is equal to 3 times 4 raised to the power of x minus 1. Remember, we're not in the table looking at the coordinates. So this means shifting a right one, as does this. And if I wanted to take a look at, what the table would look like, right, we'd have our original points would be transformed into, well, now, since we have this x minus 1, we know that everything's moving to the right one, so our x coordinates are going to be like x plus 1. And then our y coordinates look like they're going to be just 3y. So are these two things going to be equivalent transformations? I mean, these rules look completely different down here, don't they? But let's just take it and let's graph each of them and see what we get. Let's graph this, and let's graph this and see what the tables look like. All right, so let's go in and let's see, I have to clear out what's in here, and we'll do 3/4. And we're multiplying that times 4 raised to the power of x. And then we're going to go down here, we're going to say 3 times 4 raised to the power of x minus 1. Okay, so let's see what happens. We graph it and you see there's only one function, so that means they might be. Let's confirm it by looking at the table. And you see here all of our outputs. Remember, this left column is all my inputs, and the middle ones would be for my one function, and the ones on the right would be for the other function. So you see that these values all match up on the middle column and the right column, which means, yes, these transformations would be equivalent. And that's for this particular function. That doesn't mean that that's always going to be true for every function, right? If we do some sort of vertical compression and then move to the right one, okay, for some it will, for some it won't. You just have to pay attention to, your functions that you're dealing with. So if you have questions, please make sure you reach out. Otherwise, thanks for watching.